Okay, I think the question in your document is, what's the maximum potential energy? And if that's not the next question, well, it's very relevant to what we're writing down here, okay? So, maximum potential energy then is 1/2 Ka squared, where A is the amplitude, the maximum value of x. Obviously, if the potential energy is 1/2 kx squared, the maximum potential energy is going to occur when x is at its maximum. And the maximum value of x is the amplitude, for which we use the symbol capital A. Also, at this point, the kinetic energy is 0, because in reaching the maximum amplitude, the oscillator comes to rest just before beginning its return to equilibrium. Okay? And then, of course, it goes through equilibrium to maximum displacement on the other side. It keeps going back and forth. So, from the fact that the oscillator stops when it gets to the point of maximum displacement, we determine the kinetic energy at that point is 0, so that the total energy at that point is just the potential energy, which is 1/2 Ka squared. So total energy is 1/2 Ka squared. And this is not just at the point of maximum displacement, this is at every point. And how do we know that? Well, since an ideal oscillator doesn't dissipate energy, so I'll say this dissipates, and you're not going to be able to read that word, but from context, okay, you can see the dissa here, and then things kind of went to heck, but this dissipates no energy. So the total energy doesn't change. We're not adding any energy. It doesn't dissipate any energy. I should have said we're not adding energy, but that's part of the premise of the problem. Okay? Now, the question then is, what's its potential energy, or what's its kinetic energy at position x? Okay, well, we know its total energy. We know its potential energy at any position, so we certainly know the potential energy at position x. So at position x, there are two things we can say. Net force is negative kx, not necessarily relevant to the energy considerations, and potential energy is 1/2 kx squared. Okay, we know this because that's our basic premise. We know this because we integrated our force with respect to position, and this is what we've got. This is the potential energy relative to the equilibrium position. So the kinetic energy at this position is the total energy minus the potential energy. And that is, since the kinetic plus the potential is the total energy by definition of total energy, and this is constant. And here I say, since there do not exist dissipative forces. Repeating what I said up here because I didn't remember that I'd said it down here. Okay? Doesn't hurt to emphasize that twice. Okay. Well, total energy is 1/2 Ka squared, potential energy is 1/2 Kx squared, so that the kinetic energy is this, and we're trying to find the velocity at this point. Okay, that's probably why we went through the process of finding the kinetic energy. Okay, so kinetic energy is 1/2 mv squared, so now the kinetic energy equal to total energy minus potential energy says 1/2 mv squared is 1/2 Ka squared minus 1/2 Kx squared. Now, this and this have real meaning. Okay? These are connected to basic principles of energy conservation, to the basic principle of energy conservation and the energy details of the oscillator, which are really pretty simple. We can solve this for V. and we get this. Okay? Now this is very handy if you want to calculate V, and if you understand this really, really well, then you see how this is related to the energy. But otherwise, this is just a meaningless formula, and I don't much care for meaningless formulas. Okay? This has meaning, this has meaning. I advise you to stick with these things because it's really easy to solve this for V. Now, I didn't solve it for V. Of course, it's solved for V squared, but you can solve it for V. Okay, so this is worth knowing well before this is worth knowing. Now, if you want to know both, that's fine. And if you want to see the relationship, that's fine. This tells you that the kinetic energy is equal to the total energy minus the potential energy at any point x. This is a velocity at point x. Now there's more we can say about this, and we can relate this and prove that this is the case in terms of these formulas. Okay, in terms of the formulas for the position and velocity and acceleration functions, and actually only the position and velocity functions are going to be relevant. We're going to calculate all three, and that's very easy. And then we're going to verify this formula in terms of these equations to show that everything is really nice and consistent.